last time, looked at assignment 4. That's been given out. That should be accessible. Now, most of this stuff that we're going to be looking at before the end of the year, it doesn't go towards another assignment. There's no other assignment. So it's a mix between stuff that you have to do in the project and stuff that you should just know because it's a game programming class. There's no exam in this course, so you may say, okay, well, any lecture where I'm not applying that thing to the project may be a waste of time. That's one way of looking at it. Another way of looking at it is that hopefully you should want to be like good at what you do, and so information is never a bad thing. And of course, you could implement all these things in the project if you want, or not all of them, but some of them as the bonus material if you wanted to. So today, we're going to be talking about advanced main game loops, and I guess we'll just get into that. Let's do it. So lecture number 18, advanced main game loops. And just as a quick note, there was listed in the syllabus, which I'm sure nobody remembers, a couple of recommended textbooks. And one of the recommended textbooks, but not required, is this Game Programming Patterns textbook. And the material for some of the slides in this lecture is from that book. And I recommend going and looking through that book, at least at the topic list, to see if there's anything you're interested in, because it's a pretty cool book. And some of these diagrams are from that. So game loops, in the beginning, you may recall, yep?
When is the book from? What year is it?
Oh, I have no idea. It's several years old. But it's like modern enough that I listed it for this course. It's not some 1983 game programming book. It's pretty good. But yeah, I don't know the publishing date on it. So in the beginning, you may recall one of the first programs you ever wrote. So let's recall some simpler console programs you wrote while learning how to program. And those console programs like Hello World, right? So you wrote your Hello World because everyone has to do that by law in computer science. And then maybe they told you how to ask a question to the user and then get some input, right? And then maybe later on they told you how to write a user interface. And then so there was this sort of steady progression of things in a program, and the architecture changed in that program. So your initial programs that you wrote probably had something like, okay, run some initial code, print the instructions for the user to the screen, wait for some input somehow. So for example, actually I'll have an example in a second. Then after you get input from a user via the keyboard, you're going to store that user input somehow, and then you'll continue on with the program code somehow. This is in the way here. So I'm going to move this. Okay, so let's have a look at something like this. So here is our very, very simple program. So we've got some input that we want to grab from the user. And we're going to cout enter distance in feet. And this is one of the first things you probably did. Then cin input. So what this does in C++ is it reads from standard in, something that someone types in the console, stores it in input, and then you print out that is. And of course, you multiply it by 12 to go from feet to inches, and so that is this many inches. Bit of an empirical example, but it's a little bit more exciting than just multiplying everything by 10. So then we have this while true loop here. So this program, very, very basic, just really wants to know feet, and then really, really wants to print inches, right? That is a program that has a very dedicated purpose. And then it doesn't even, it wants to do this so much, it doesn't even have a quit option, right? So maybe, you'd put something in here that says enter Q to quit or type 0 to quit. But right now, you've just got to close the window or Control C or something like that, right? So here is that program structure in a nutshell, which is at first, you're going to display some instructions, maybe, just some print statements to the program. And then you'll have this loop, which does the bulk of the work of the program, right? Because most programs that aren't just doing a calculation are interacting with the user somehow, And so basically what we do is we wait for some input from the user. This is a blocking call, and that's an important distinction. A blocking call means that nothing happens until the user gives that input, right? So that's a blocking call. And then you do something interesting with the input that you receive from the user, and then possibly display more instructions or quit or whatever, right? So this is our first real introduction to the main loop. And we're talking about game loops, but there are loops that control the structure of most programs, not just games, right? So there are some things that are a bit unique to games, but it all started back in the first program. So even more modern GUIs follow the same basic structure, since really nothing in the user interface changes unless the user inputs a value. So for example, let's look at a word processor like Word, or is there even another word processor out there now? Google Sheets, I guess, something like that. So in a word processor, you're going to display the current document, then wait for the user to type or click something, probably, because if the user isn't typing anything, there's no real need to update the screen. Now, okay, we can think of more modern examples where there might be, but in general, if they haven't typed, then the document hasn't changed, so just keep displaying the same document. Then handle the user input somehow, and then repeat, right? So what does that look like? Well, we're going to start up the initial user interface. So when you double-click on Microsoft Word, I'm not saying this is how Word works, obviously, but it's just an analogy. So display some sort of initial user interface. You've got Clippy there on the screen. You've got like Go by Windows 11 or whatever they put on the screen when you first launch it. Then you've got some user interface which maybe has some buttons on it. It maybe has a blank document on it. And so you poll for user input events. You update internal variables based on that input. And then you update the user interface based on the internal state of those variables. So for example, you've got a blank Word document. Let's say you've got the simplest possible word processor where all you can do is type on a screen and then print it, for example, no saving. I have actually used one of those back in the day. So you just display an initial UI. You're typing. You're waiting for user inputs. The user types on the screen. You update some internal array with the contents of what the user has typed in. And then right after they type, now you are constantly displaying whatever the contents of the things that the user typed in. So again, we're just illustrating here that we're getting a little bit more complex with our loop here. So, but unlike other programs, now I've kind of cherry-picked those examples. Unlike other programs, games keep moving when the user doesn't input, or at least most games do. If we're writing like a chess program, right, we probably don't need to update the UI or anything while the user is moving, but maybe if we have a clock, we do, or something. But you can say, okay, if this is not a turn-based game, then the games typically keep moving, right? Like, the game won't be paused just because the user isn't doing anything. And so the clock keeps ticking, the NPCs keep moving, the animations keep animating, and the key here is that we don't wait for the user input. And so the user input call is not a blocking call, right? Every tick, we're just essentially going to say, hey, if there's some input, process the input. But if you're just standing there as Mario, well, the Goomba is going to walk into you, right? The game doesn't say, oh, they're not doing anything, therefore I should stop or wait for input. So what does this look like now? Okay, well, we have some initial UI on the screen. Maybe that's the start state of the game, and then you've chosen to play the game or whatever. And then while true, process the user input if any input exists, update the internal game simulation by one step, and then render the current game screen, right? So this is what we've been looking at since assignment 1, basically. So in assignment 1, what do we have as controls? Did we have like pressing the X button or something? Do you remember? Or was it just bouncing off the sides of the screen? Did anyone do assignment 1? Do you recall? Just bouncing? Okay, I think in my demo program I just had the X button reversed something. But this basically has been what we've been doing the whole class, at least on assignment 2, 3, and 4, right? So process the user input if there is any, then update the internal game simulation, and then render the current screen. So this is what this basically is with our current game engine. While true, process the user input, update the game engine somehow, and then render the game to the screen. And so in this case, we have our updates and our rendering kind of in lockstep, right? So it's input, update, render. Input, update, render. Input, update, render every single time. And that update could be kind of complex, right? So in our game engine, we're not as complex as like a more modern game, but we do have some stuff going on here. So for example, in our update function in assignment 4, we don't actually have a user input in our scenes update anymore, but I just put it here because it's what we did and basically what we're doing. So we have our user input system, that is the process input stage. Then we have entity manager update, AI update, movement system, lifespan system, collision system, maybe updating the state of the animations. So all of this is the update step, and then we have our rendering step down at the bottom, right? So even though, this you say, oh, that's not very complex, well, it can be as complex as you want, and this is basically what we're doing throughout the course. So that's kind of caught us up to where we are, and now we're going to talk about issues that can arise with this architecture, improvements to this architecture, how to solve issues that we run into with this architecture. So when programs use blocking input, they can run the loop at any speed, right? So back in that, feet and inches program, or the Celsius Fahrenheit program, or whatever your first program was, you don't have to worry about how fast that main loop is running. You can just say while true, because that input is blocking, which means that you're running at the speed of the user. So if the user takes a minute to type something in, well, you didn't want to run faster than a minute because then the user wouldn't have been able to type in their thing, right? And if the user takes 5 seconds to input it, you wouldn't want to wait the full minute because then the user would be frustrated with your program. So it's a blocking call. It's literally just waiting for the user to input something. And so you don't need to worry about that main loop's speed. But with non-blocking input in something like a game loop, now we do need to decide how fast that loop spins. And that's going to have dramatic effects on how the game runs. So each update, for example, what we're currently doing with our engine is that it advances the game world by the same amount each call. So for example, if our player has a speed of 5, meaning that every update call, we want to advance the user's position by 5, then if that game loop is running at 1 frame per second or 60 frames a second, the game is going to feel much different, right? So at 1 frame per second, it's going to be unbearably slow, and at 1,000 frames per second, well, things are just going to be so fast that you can't control it, right? And so the game world clock ticks forward by 1 each time we call this update. And the thing is, the player's real-world clock is ticking at a different speed. So what this means is that when we design our game, like let's say we're making, assignment 4, we've got some sort of notion that the world of Link is moving at approximately the same speed as the world of the user, right? Because we could make it run as slow or as fast as we want. We could have Link in slow motion running around the world, but that's not very exciting. And we could have them running 1,000 times as fast, but then it's completely uncontrollable. And so as the game designer, we have some sort of idea of, okay, when I press up, I want it to be moving this fast on the screen, right? And so the game world and the physical real world do tick at different speeds, right? We could run Link at, 100,000 frames a second. It's not a very complex calculation, but that would be bad. And so how many game loop cycles in 1 second determine the game's frame per second count? And so if we just say while true on our game engine, we're going to be limited by one of a few different things, right? So for example, here, if all we did was say, while true, process input, update, and render. And we didn't have any FPS limiter in SFML or however we're doing it. This is just going to run as fast as our computer can run this. So if we're running this on an NES or a 486 versus like, you know, a 13th gen i9 or whatever the most fancy processor is these days, it's going to have wildly different results. And typically, if you make a game, you want it to be playing the same on everyone's system, right? Or at least somewhat the same. Like you can have, okay, maybe this person's computer is better, so the graphics could be better, but you still want both users to be like Mario running around at the same speed. So what we've been doing to control this so far is that we're setting a frame per second limit. Now we're kind of cheating in that we're letting SFML do that for us, but if we have 60 loop calls per second, then that's 60 rendering calls and 60 update calls, which is 60 frames per second, right? But basically what I'm saying here is now we are in control of how fast this game world moves, and we really do need to control this. So typically, more frames per second means smoother play. So we would ideally like to display as many frames per second of the game to the user as possible. And these frames per second are typically determined by two things. One, how much work is done by the CPU on each game loop, and how fast is the underlying hardware, right? Like, so if we've got a billion cycles worth of stuff to do, and we can do a billion cycles per second, then we are running at 1 frame per second. And so it's a combination of how much stuff needs to be done by the CPU and GPU, and how fast the underlying hardware was. Older games had kind of an advantage, especially with console games, of knowing the exact hardware that it would be run on, right? And so they knew how fast the game would run. So if you're doing something like Atari programming or like NES programming, there's no like waiting. The screen is just like, well, at least with the Atari, it's just like rendering out, and you have to make sure that the stuff that you want the user to see is in the right position at the right time. So that was an advantage in one case because you knew exactly how fast that clock was ticking, and it will never change, but it's a disadvantage because it makes it kind of harder to program. But modern computer games run on a variety of hardware, and so of course we have to accommodate for that. So the flexibility that you have with your game loops can depend on many different factors. So whether how we're going to be able to control these depends on a bunch of things. So for example, your operating system. How often can you actually pull events in your operating system? This may affect how many times you can get user input. Are your hardware input events blocking, right? So if you're using a blocking call like standard cin versus poll event, that's going to have wildly different results. Maybe you have a monitor that has to have vsync, right? So if you have to enforce vsync, then your frames per second of your game is limited to the refresh rate of your monitor, right? Maybe you have, if you're talking about something like networking, maybe the type and speed of your network traffic determines how often you can update something in your game. Now, most modern hardware, we don't really have to think about these things, especially if we're using like a game engine, right? It just kind of does all these things for us. But, you know, they're worth mentioning because they were a thing in the past, even if they're not so much of a thing in the present. So let's say that we do want to implement a fixed FPS count. Now, you might say, well, we're using SFML, so we can just do what we have been doing. Why are you giving this lecture? Well, the problem arises when problems arise, and that no longer meets your needs, right? So let's say we want to fix the game at 60 frames per second. So note, we've just been cheating and getting SFML to do this for us. But to do it manually, what we would do is limit our game loop to run at most every 16 or so milliseconds. So 1,000 divided by 60 is 16.6666 or something like that. And so approximately once every 16 milliseconds, we would allow our game loop to run. And so the point being here that if our update and rendering takes more than 16 milliseconds, then you've got a problem, right? because if the stuff you want to do every frame takes longer than 16 milliseconds, well, then you're screwed from the start. If it takes 100 milliseconds to do all your stuff, then you're never getting to 60 frames a second, right? And so we're starting with the assumption here that the stuff you have to do can actually be done in the 60 frames per second. So what we do here, and this is exactly what SFML does, is we, at each frame of our game, we process the user input, and this diagram is straight from the book. So we process the user input, we update the internal state of our game engine, and in our class that's done with the systems, and then we render it out. And once this has all been done, let's say that takes 3 milliseconds, for example, then we're going to just wait for 13 milliseconds. And so we want this to take 16 milliseconds every single time. Now, where exactly you put this sleep is dependent. Like, you could put the sleep right before the rendering. So for example, maybe you know, okay, I'm going to have a variable amount of time in between. Some frames are going to take 6 milliseconds. Sometimes it'll be 3 milliseconds. And so what we could do is put the waiting before the rendering or after the rendering. But essentially the thing we're doing is figuring out how long it took to do the stuff and then waiting the remainder of the time. So if we look at this in code, okay, let's figure out the amount of time that we have to wait. So this 60.0 here, that's the frames per second that we want to hit. Then here we have our main game loop. Then we're going to say, okay, our starting time is the current time in milliseconds. Then we're going to process the input, update the internal game state, render the screen, and then we're going to say, okay, we have the time that we started doing this, we have the time that it currently is, subtract the starting time from the current time, and we have the elapsed time. And now I'm going to sleep for a maximum of 0 and milliseconds per frame minus elapsed. And so what this says is, however many milliseconds per frame that we wanted, so for example, let's say it was 16, and if this took 3, then that will be 13. However, if this ended up being negative, meaning that we actually had like a lag frame, right? So we wanted it to be 16, but it was 50. Well, how do we sleep for negative 37 milliseconds? We can't do that, right? So we just put this little max in here. So we sleep for as much time as we need to, but we could still be slowing down, right? But we'll talk about that in a bit. Oh, I'm about to talk about it right now. So adding the sleep to the end of the loop ensures that we don't update too quickly. And how sleep is implemented on different architectures is different. Sometimes your programming language or your operating system, they all do different things. Whether or not this sleep command, depending on the language, the OS, that may be 100% CPU usage. It may be like a while, and then it just may be a while loop that you're checking for something all the time, or some other way that the operating system has of timing sleeps. Also, the accuracy of a sleep call may be different on different systems. And so I know, for example, I've used systems where you have like a 10 millisecond accuracy on sleep. So you can't sleep for 13 milliseconds. Now, modern hardware, there's usually decent ways to call sleep or call, to wait for the amount of time that you have. So sleep, I'm putting in here as a placeholder for the most accurate way that's available to you to wait a specific amount of time. Okay, so whether that's a busy sleep or a passive sleep or whatever you have in your operating system, investigate that way of doing it beforehand.
Never mind, you already answered.
Okay. So unfortunately, though, we can make sure that we don't do it too quickly, but there's no way to ensure that slow code doesn't make your game run too slowly, right? So I could prevent too many students from coming into the classroom, but that's not the problem that we're having, right? I can't force people to come to the classroom. So that's kind of the opposite problem. But there's like setting the FPS counter, if it isn't obvious to you already, doesn't say your game is going to run at 60 frames per second. There's no magic way to do that, to speed up your code. But if it was going to run faster, it can certainly slow it down. So in this case, well, you've just got to cut your computation, right? So where we had that right here, maybe your update or your rendering could be slow sometimes, right? And I'm sure you have all played a game where it was slow sometimes, right? And you just see this like stuttering in the gameplay. If it's, 16 milliseconds per frame and you're used to that, and then all of a sudden there's a bunch of stuff on the screen, and so the calculations take longer, now maybe you're running at 30 frames per second for a few frames. So, a quick note on SFML. We've been calling set frame limit, and this is basically what it has been doing. And so it limits the frame rate to a maximum, and I'll just read what it does. So if a limit is set, the window will use a small delay after each call to display to ensure that the current frame lasted long enough to match the frame rate limit. SFML will try to match the given limit as much as it can, but since it internally uses SF sleep, whose precision depends on the underlying operating system, the results may be a little imprecise as well. For example, you could get 65 frames per second when requesting 60, etc. So just keep in mind that this is an actual thing that we have to deal with, which is the timing of the operating system, etc. All right, so just some quick notes before I go to the next slide. We're going to deal with what happens if we do have lag, right? Which involves a game design decision and an implementation decision. So the following slides will show different ways that you could catch up after lag frames. In some cases, we want to do this, and in other cases, we actually don't want to do this. So the slides are going to show you one way, actually a couple of different ways, to implement different techniques in your game engine if this is your goal. And so what I mean by this is, let's say 3 or 4 frames in a row, it took maybe 100 milliseconds to update your game, right? So if you're in a sustained period where your calculations are going to take too long, maybe it's like a second, or maybe it's half a second, or a tenth of a second, or whatever, you've got some frames that are taking too long, right? So once the lag is over, so maybe you've fired a rocket at all the NPCs that were slowing down your game, or the particles are gone, or whatever it is, you've got 2 decisions to make, right? One is, like old NES games, do you want to just say, okay, well, it's going to run slow for a little bit, and so if your game was supposed to progress like 10 seconds in the game world, that's supposed to happen in 10 seconds in the real world, right? But if you're playing like GoldenEye, for example, for the N64, there's lots of lag in that game sometimes. So if I'm running through the train level and there's a bunch of explosions and crazy crap going on, that 10 seconds that was supposed to elapse in the game world, that actually took me like 15 seconds in the real world because I noted this slowdown, right? So do I want to just keep going from where the lag ended, or do I want the game engine to kind of keep up and then like fast forward itself to the point where I'm supposed to be now, right? Now, if you have that case where there's like multiple seconds being missed, that's kind of jarring. Maybe you don't want to do that. But if there's just a few milliseconds for a few frames, right, do you want to just continue on from where the lag happened, or do you actually want to catch the game up to where the simulation is, which would be pretty necessary if you're doing something like networking, for example. And so that's a game design decision, right? Older games, they just say, well, it's just going to be slow for a bit, and then we'll keep going from when the slowness ends. But in more modern games, maybe we have some different solutions to that. So the first one that I'm going to show is called game simulation scaling. So the problem that I just talked about is that each update advances the game time by some amount, right? So we've got 10 seconds of GoldenEye that passes, but it takes some amount of real time to compute that. And so inside the GoldenEye game engine, it's saying, okay, well, this frame was less than 16 milliseconds, so I'm going to wait. And so if that happens, our 10 seconds of GoldenEye time is going to take 10 seconds of real time. But if those frames in GoldenEye have lag, then the 10 seconds of GoldenEye time are going to take longer than 10 seconds in the real world. We're not going to have shorter than 10 seconds in the real world because we've guaranteed a frame limit, but we could take longer than that. So if 2 takes longer than 1, then the game slows down, right? There's nothing we can do about the game slowing down. So for example, if it takes longer than 16 milliseconds to update the game world by that 16 millisecond equivalent, then we can't keep up. So if we could somehow advance the game world by more than 16 milliseconds, then we could update less frequently and keep up to date. So what we could do is introduce a variable that we will use to update the game world simulation. And this is called a variable time step. And essentially what we're going to do is inside our update function, before, where let's say our user's speed was 5, right? And so it was doing 5 per frame. Now we actually have a variable which is saying how much time we want to pass in our game world for the update, right? So let's say Mario's speed is 5 meters per second, or 1 meter per second, or however fast Mario runs in real world equivalent. Then if it was 1 meter per second, and we said, okay, update for 1 second, he'll run 1 meter, and then we'll render. But if we said update 3 seconds, it will multiply 3 by the speed and move Mario that far, and in one update we'll have gone farther than we would have in a normal update. Okay? So this is introducing a variable to the game simulation that says how far into the future we want to run. So each frame, we're going to calculate how much real time has passed since the last game update. What do I mean by that? Well, we'll see in the pseudocode. When we update the game state, we're going to use the real elapsed time as a scaling variable. So, for example, if we have a bullet flying through the air, each time step update it with the velocity, but with variable time, you're going to scale the velocity with the updated time. So far in our game engine, we've just been saying, okay, we're going to assume that every single update is the same amount of game time that's elapsing, regardless of how much real time that takes to compute. But here this is saying, no, let's actually take the amount of time it took to compute this, and then on the next frame, that's how much time we're going to say has elapsed. So the advantages to this is that the game is going to look to play at a consistent rate, regardless of how much hardware that we have, or the speed of our hardware. But if a player does have a faster machine, they're going to get a smoother amount of frames per second. So for example, this way, what could happen is we no longer necessarily need to wait between frames, right? So if my computer can run 1,000 frames per second, then I'm just passing in a smaller variable into the game engine. If you can only run 100 frames per second, then I'm passing a larger variable into the game engine. So the things in my game engine are moving a smaller amount per game tick. The things in your game engine are moving a larger amount per game tick. However, this is a possible solution. I do not recommend this solution because the disadvantages, in my opinion, outweigh the advantages. So this variable time step stuff. This comes from, it's more done in like physical simulations, right? Like if you wanted to do an actual simulation of like a real world phenomenon, like, I don't know, some lava flow or fluid dynamics or whatever, there you're going to have to decide on a time step, right? Like what has happened in 10 seconds? Well, I'm going to have to decide on a time step, and this could keep your simulation running in real time, maybe something like that. But we introduce a non-deterministic effect into our game engine based on this variable frames per second, right? So who has ever tried to, if you say float x equals 0.2, and then you print x, what gets printed? Yeah? Yeah, so floating point errors are a real thing, right? And, okay, if I have 0.00002, who cares? Well, that may have been the difference between a collision happening or not, right? So in one person's game engine, they got a collision, and in the other game engine, it didn't. Or, over the course of many, 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 many frames, 0.0002 starts to add up, right? And so the error may be very different by the time you get to, hours into this game or something. And so what happens is, on your computer, you may have run for 3.6 milliseconds. On my computer, I may have run for 4.2 milliseconds. And so I'm passing in this 4.2 that everything gets multiplied by. You're passing in this 3.6 that everything gets multiplied by. And, you know, it is not the case, and 0.2 is a good example, that in a computer, 0.2 times 5 is not equal to 1. Right? And so we're not necessarily going to get the same results from this. You can have all sorts of problems like network desynchronization, physics simulations yielding completely different results. I've actually had this happen where I ran a simulation like it had to go for like, let's say, the equivalent of 10 minutes. So what I did was I said, while the simulation is not at 10 minutes, we're going to do, okay, I want this to be like a test run, so pass in like 100 milliseconds as the time step, right? So if it had to go for, did I say 10 seconds or 10 minutes? Minutes, okay. So we have 100 milliseconds, which is 10 of those per second, and then we have 600 seconds, so 6,000 updates. That's how long it took to run it, right? But then I was like, okay, next time I'm going to pass in 1 millisecond per frame. So now I'm going to do 100 times more work. So instead of 6,000 updates, it was 600,000 updates. But because the extra precision of doing more time steps, different collisions may have happened, and even though theoretically I should have gotten the same result, I actually got like a drastically different result. Okay, so even though theoretically you'd think that 5 times 0.2 is equal to 1, that is not necessarily the case. But what it would look like if you did do something like this is that you're going to calculate, okay, current minus last time. So this is the amount of time that our last frame took, and that is elapsed here. And then you're going to update your game engine based on elapsed. And so if you can run this loop faster, then elapsed is going to be smaller. If you can't run it as fast, it's going to be slower. But we no longer have this FPS thing, right? So we've completely eliminated the need for worrying about frames per second because you're just updating it as fast as possible. So if floating point error wasn't a thing in some magical world, this would just be how we would do everything, right? Because there'd be no problems with it. We wouldn't have to worry about FPS. It would just run as fast as your computer could run it. And on different hardware, our game, like Mario, the updates would be different, but Mario would be running at the same speed on your old crappy hardware or my really new good hardware, right? And we don't need to worry about FPS. But because of those issues, it's not used a lot in practice. Now, some game engines do. They may use something like this in their internal physics simulations, but I wouldn't recommend it for the project, right? I'm just showing you that there are advantages and disadvantages to these systems. All right, how does rendering fit into all of this? So whether or not we use variable time steps, rendering is not affected, right? Rendering essentially just takes the current state of the game and draws it. Rendering doesn't care what our game state looks like or how often we're updating the game state. It just takes the game state and draws it to the screen. But that does take some amount of time. So instead of variably updating the game simulation, let's render at different times. Maybe that could be a possible solution. And so what this is going to do is it's going to allow us to get back to fixed game time steps. So what this means is that we're going to, and again, this is a case of making up for some lag that has probably happened in the past. So let's say that our game update typically takes 1 millisecond. So we'd be processing input, updating the game, rendering, wait for 15 milliseconds, right? One way that we could catch up instead is if one frame took a bunch of time, and then we didn't have to wait. If we want to catch the game state up to where we should render the next time, well, if this is only supposed to take 1 millisecond, we can just do a bunch of game updates, right? So now what we're doing is multiple game updates. So instead of saying, for example, normally our game engine processes 1 millisecond of game time, right? So in the variable time step thing, what we would do is say, okay, instead of doing 1 millisecond this time, do 100 milliseconds. So instead of multiplying everything by 0.001, now it multiplies it by 0.1, right? Here what we're going to say is, hey, those different calculations where 5 times 0.2 doesn't equal 0.1, that's a terrible thing, right? So what we're going to do here is we're going to say, okay, I'm going to keep a fixed time step update. So I know that I'm always going to be update with a fixed time step of 16 milliseconds or whatever. You know, Mario's always going to be moving by 5. But instead of saying simulate the game for longer, the way I'm going to accomplish that longer simulation is by just calling multiple simulations of the same thing. And in this way, it gets me back to that fixed update, so I no longer have that error that's caused by those floating point things, but I can also catch up to where I was. So let's look at a real-world analogy. I'm very proud of this analogy, by the way, so I hope you appreciate it. All right. It's a fast food analogy. So you're tasked, hopefully you don't have to encounter this analogy, but you're working at a fast food joint, and you're tasked to make a cheeseburger every minute at a fast food place, right? So this is the game step update, right? The game engine is trying to update something every minute. It takes you about 15 seconds to make a cheeseburger. That's pretty impressive, right? And so you've got 45 seconds to rest between each cheeseburger. If your boss just wants one a minute, then you can make one, and then you can rest for 45 seconds. But you're not perfect, so one burger slips and falls, and instead of picking it up and giving it to the customer, you're going to throw it away, and it takes you 2 minutes to clean it up, right? So now you're behind by 2 minutes. All right, what do you do? Well, since you can make 4 burgers per minute, you can catch up by making 3 burgers in the next minute, right? So in case that didn't sell you on it, I've got a diagram, okay? So, desired 1 burger per minute. This is what you desire to have happen. So, you've got 60 seconds between burgers, but it only takes you 15 seconds to make a burger, all right? And then 45 seconds. If my face is covering up the top right on the video, it just says 45 seconds here. So here's what we have. We have this, our game step update, our burger step update is that our processing of the burger takes 15 seconds. Oh, come on, Ben, don't cry. It's not that bad. And then you've got 45 seconds where you can rest. But here, we have the accident, right? I made the first burger, but then I had a 2-minute accident here, and now I've got to catch up. And so how do I catch up? By making more burgers that I have time to on the next time step, okay? So now what happens is, if there's a little bit of lag, and this works if the lag is like sort of imperceptible, right? If this is multiple seconds of lag, we don't necessarily want to catch up by 10 seconds. But if I have a game running over here, and you have a game running over here, ideally, both of us, after playing for 5 minutes, you don't want this game to be running slower than that game just because there was some enemies, like there were more enemies, they didn't kill them fast enough or something, right? So here's the algorithm for this burger update. We've got, we're going to keep track of how much time things have taken, so we're going to have this previous time. And then we're also going to keep track of how much lag we have. And that lag is like the 2 minutes. So the 2 minutes that I dropped the burger, that is that lag. Okay, so while true, we've got our main loop here. We're going to say current, that is the get current time, and then the elapsed amount of time is current minus the previous, right? So whatever the previous was, well, we're about to set previous equal to current, but this calculation gives us how long the last one took, right? And so if we had a 2-minute burger mistake, this is going to be 2 minutes. Now, we're going to add that amount of lag to elapsed, because lag could be, we're going to take elapsed and add it to lag. And the reason why we're adding it to this persistent variable is because lag can add up over time, right? Maybe I make a 2-minute mistake and then another 2-minute mistake, and now I've got to make 5 or 6 burgers, right? So, but if I've got to make 6 burgers and I can only make 4 a minute, then I can't catch up everything on one frame, so I've got to persistently store how much I need to catch up. So then we process the input, and then, while lag is greater than milliseconds per frame, right, I'd call the update and then subtract the milliseconds per update. And so what does this mean? Well, every burger that I make during this time step, before I render again, before that minute is up, I'm subtracting the amount of time from the lag that it took to make the burger, right? And then once that's done, I render. So what that little loop here did was say, okay, I've got that 2 minutes. I'm going to make another burger. And every time I make a burger, I subtract a minute from the amount that I have to catch up because that was the amount of time that I was supposed to take to make a burger, right? So the milliseconds per frame, that's the 1 minute in the burger analogy. So what does this do? Well, the lag measures how far behind the game's clock is, behind the real-world clock, right? So that's the burger lag. The inner loop updates the game to catch up until all of the lag is gone with fixed time steps. And then once we catch up, we render the scene. And so the game simulates at a constant rate using fixed time steps, which is a safe way to catch up for those lag frames, right? Because if I was always updating with 5 for Mario's time, now instead of saying, okay, this is 5 times 4.1, right? Now I'm just doing 5 4 times. And so I would have gotten to the same place. And so rendering may appear choppy while the game catches up, but at least the simulation speed is fixed on different hardware. And note that we can only catch up if these sort of lag frames are infrequent. If you keep dropping burgers, you're never going to get back to your 1 burger a minute thing, right? So, now you know. All right. Another thing you could do is decouple the rendering from the whole process, right? So, what we've done now is we've removed the synchronization of update from rendering. Because before, every single render had exactly 1 update. But now, we could have multiple updates per render. So we're no longer calling 1 render per update. This means we could, if you want to, put rendering into another thread. Something like that. But some issues can arise for this, like maybe if you could do rendering between updates, okay, maybe now I have to store a second game state to make sure that if this thread is my game state update actually thread safe, when I try and render, now I have to block, and there's like, we're not getting into multi-threading architectures and stuff in this course. It's way too much. We'd spend the whole course on that. But essentially, what we could do as another potential fix to this system is just render at different times, right? And so the rendering and the updates, maybe this render took a long time, this render took a variable amount of time, okay? So if we do render between updates, then maybe one of those updates wasn't finished. And so the game could actually look the same for 2 frames in a row. And that would, look like it was laggy. And so what we could do is do some interpolation, basic movement calculations inside the rendering. Like now what you could have is like the rendering system could be doing interpolation and stuff. There's so many different things that modern games do that like try and fake the fact that, oh, the game engine update had some lag, but we do have the positions of the things on the screen now, and we had the positions of the things on the screen before, so maybe the rendering system guesses at where the things are next, right, and just draws them there, but then once the game state actually catches up, then it renders the proper thing again. So there's all sorts of crazy stuff that we could do. The physics may not be exact in this render, but at least the game world will be exact in a future render, just telling you that this exists, and we're not going to touch that with a 10-foot pole. All right. So we talked in the past that this could be a problem, but now we're going to actually look at what is going to happen, is that given our basic way of doing collision detection, we're just saying, is there a collision? Move the thing. Is there a collision? Move the thing. Is there a collision? Move the thing. It's by far the fastest way of doing it. One way we could do things is say, we are here with this velocity, here are the positions of everything else, calculate the exact time at which there might be a collision, right? If we were doing some advanced solar system physics simulation, maybe we'd do it like that. But right now we're just saying, okay, here's a bullet. Is it hitting a wall? No. Is it hitting a wall? No. Is it hitting a wall? No. So giving our basic way of doing collision detection, an entity going fast enough could pass through a game tile. So for example, a bullet could shoot right through a wall. Now, what we have to do in this case in our game engine is something really hacky, which is saying basically make it so that the bullet or any entity can't move faster on one frame than our skinniest tile. That's basically what we have to do, right? But what if we want a bullet that goes really fast? Well, sorry, you just can't have it in your game engine, right? Because it could go through a wall, and that would be terrible. And so what we kind of did is this hacky solution of having a maximum speed for entities, right, where the bullet can't go through the wall because we've just said, hey, the bullet's speed is less than the minimum wall size. But as long as the maximum speed is less than the thickness of the smallest tile, it works. But what if we want our entities in the game to go at faster speeds than that allows, right? There is something about our game engine which is very limiting, and this is one of the things that is very limiting. So what we can do is have multiple update loops. And so this is actually something you can do quite easily in your game engine, because at one point it calls update, and another point it calls render. You could just say, okay, let's update multiple times. So what you might have to do in that case, so one simple solution is to increase the number of game ticks per second. So, for example, we want the max player speed to be 100 pixels per frame, right? So if we want the maximum player speed to be 100 pixels per frame, like rendering frame, the tile size is a fixed 32 pixels. Well, this means that the player can move way through a tile. It could just teleport from one side of a tile to another side of a tile. But if we do a little bit of math and we see, okay, our tile is a fixed 32 pixels, if instead of every single update in lockstep with rendering being 100 frames, 100 frames, 100 frames per render, we could instead say, okay, we're going to fix the player speed to 25 and update the game world 4 times between each render. That way, our maximum speed is still less than the thinnest tile, but it looks to the user like Mario is running at the fast speed that we want. Okay? And so what we're doing here is we're trading some CPU effort for simulation accuracy. So you have to be aware that, okay, well, if we're doing 4 times as many updates, that's going to be 4 times the amount of time. And so your update function better be pretty fast if you want to do something like this. So what we had before, or currently in our game engine, let's say this pipe over here is, however, it's 64 pixels wide, and we want Mario to move at 100 per frame. Well, that's 100, that's another 100, that's another 100. There we go. We've moved through a pipe. That's not very good. We want Mario to be able to get the star and run super fast and not go through these things. So what we do is, and so that's what would have happened, but now every time the game is rendered, which are represented by these gray bars, we are actually doing 4 25-pixel updates between each one, right? And now Mario, in our game simulation, actually does properly hit that tile. And so that's what we would do. Here, I have some videos which I highly recommend watching. These are excellent videos. So this is Pan and Coke on YouTube. He has multiple PhDs in Mario 64. It is absolutely insane. Like, they've done more work on Mario 64 than I've done in my life. Like, it's an insane amount of work. So what we're going to do is we're actually going to watch one of these videos now. I'm going to cut it off of the recording so that I don't just freeboot these videos or whatever, but we have a bit of time. So I'm going to watch coin falling through floor, but I really want you to go watch walls, ceilings, and floors at the very least, because it shows you how the Mario 64 custom game engine deals with all of these things. And it's in 3D, but it's such a crazy, hacked up, custom solution that wouldn't work in any other game, but it works for Mario 64, right? And explains all the BLJ jumping and how you get through ceilings and all sorts of stuff like that. So that's a great one. And also this Parallel Universes video, which some of you may know the memes that came out of this video, but this is another one where it shows that like the rendering in Mario 64 is only done at a certain area, but like you can wrap over the integers if you get going fast enough. And so like if you wrap over the integers, then if you're outside of this range of integers, you're still in the level, but you're no longer colliding with things. So you can like get through stuff that you couldn't get through if you were in the normal universe, but now it's insane. It's like if you were just like, if you're sitting down to eat a sandwich and you want to kill 20 minutes, instead of watching some Twitch stream, trust me, you won't regret watching that video. So let's watch this, this first video here, because I think it's worth watching and it illustrates this point pretty well. I hope my sound does not deafen you. I will try and change it as soon as possible.
I couldn't save that. Oh my god, never mind. Dear Lord, die. I'm missing a coin? I'm missing a coin. Where? Where did I miss a coin?
So for those of you who are not familiar with Mario 64 speedrunning, you get, the cheese is doing 120 star speedruns. You need to get every single star. And at every level, there is a 100 star coin, or 100 coin star. So up in the top right, or yeah, in the top middle, you see that he has 63 coins, but he's so good at speedrunning, he knows that he's supposed to have 64 right now. And so at one point, if you kill this thing, you're supposed to get 5 coins, but he only collected 4, and now this throws the whole speed run out because he doesn't have enough coins to get the star. So this is actually like, oh, who cares if you just got 1 coin? Well, it changes the route of the level, and something that may have been a world record is now not. So it's actually kind of a big deal. And pay attention to the stuff on the bottom.
Dear Lord.
So here he kills Lack 2. 5
Die.
coins come out. But he only collects 4. So, he's saying here, just to give more context to what we were just talking about, unlike Mario, objects don't move in quarter steps. What I just showed in the slides was the quarter step example. So in Mario 64, Mario's physics are updated 4 times per frame. And then it's rendered. 4 times, then it's rendered. That allows Mario to be more accurately physically simulated. But who cares about coins? Right? They're just bouncing around. It's not so important to, we don't want to have to do quarter steps for everything in the game world. Right? So even Mario 64 did the hacky thing of making sure the speed wasn't bigger than the biggest thing. Imagine debugging this. So they did think of that, right? Which is insane. So like 5 of these conditions had to be true under the exact placement of a coin in order for that to happen. So you're going to have to come to that point when you do debugging in your games as well, right? One of the testers is going to be like, what happened here, right? And you can start to see, even in the simple games that you're making, like how stuff like this can happen and why it can be really frustrating.